5.1 starts with an investigation. So again, what we're talking about this whole unit is going to be modeling using graphing. So most of what we've done so far is linear, which means all of the relations that we have. Remember, a relation is something where there's two variables and they're related, and it's typically can be expressed as an equation. So like y on one side and x on the other side, or time on one side and distance on the other side. D relates to t, and we can graph that relationship. So that's what we're working on. Your investigation on page 6, 5.1, direct variation. You're going to learn what that means as we go. But Suzanne can jog, there's a typo, Suzanne can jog a steady pace of 150 meters per minute for 1 hour. Okay, so picture it in your head. She can jog for an hour and keep the same pace. Okay? A, create a table of values showing the distance that Suzanne jogged in 0 minutes, 1 minute, 2 minutes, and so on, all the way down to 10 minutes. I don't think there's enough lines for 10, but we might get there. So let's do A first. You have a table of values there, and you have two boxes at the top of your table of values. What are we relating to each other?
Time versus distance.
We're doing time and distance. So in your top left, we've got time. And in the top right, we have distance. Okay, and we're going to fill those in for 0 minutes. For time, it's going to be measured in minutes. It's 0, 1, 2, 3, 4, 5, all the way down to 10.
We only have 9.
Take out 0.
Yep. Nope, do not take out 0. You won't have 10, that's fine. You can go from 0 to 9. And we want to show what distance she's run at each of those times. So after 0 minutes, how far has she run?
0.
She's run 0 meters. Okay? So we can also note that distance is measured in meters and time is measured in minutes. And what about after 1 minute? How far has she jogged? 150 meters. What about 2 minutes? Go ahead and fill out the rest of the chart. You can check on the board after you're done. And your chart should look something like my chart. A quick way to do that on the calculator is 0 plus 150, and then you just hit equals, and it'll say 150. And if you hit equals again, it'll go 300. If you hit equals again, it'll go 450.
Mine does. But I like to use half of my brain. Yeah, that's fine.
Otherwise, you should just, do it mentally. Okay, we're going to talk about B. Whenever you have a relation, one of the variables will change in relation to the other variable. So one of them depends on the other one, making the other one independent. So one of them changes, on its own, based on nothing. But the other one changes based on the other variable. So out of these things, time and distance, which one do you think is dependent on the other one, and which one does not depend on anything? Maddie.
Distance is dependent on time.
Alright, so here, however you mark this on yours, you've got distance is going to be dependent, and time is going to be independent. That's typically going to be the case whenever time is involved. Time doesn't depend on you running. It's going to be 1 minute, 2 minute, 3 minute, whether you run or not. Okay? But if you're running 150 meters per minute, then how far you get will depend on how long you've run for. Makes sense. Okay? Good. And now we get to graph the relation. So I am going to pull out the book so that you can kind of see it at the same way. And the first thing we're going to do is draw our axes. Okay? So it makes sense to give ourselves a bit of space. I left 2 boxes to the outside on the left, and I'm going to do the same at the bottom. I'm going to leave 2 boxes. Now, which variable goes on my horizontal axis, my dependent or my independent? Horizontal is across, always going to be our independent. So this is going to be our time. So we always properly label things. We'll put time down there in the corner. And we're starting at 0, and we're just going to count by ones. 1, 2, 3, 4. Good. All the way up to 10. And our vertical axis is going to be labeled distance, or just D. And we need to get up to 1500-ish. Let's see what happens if we count by twos. If we go 200, 300, 400, 600, 800, 1000, 1200, that'll work. So let's count by 200s.
We gotta do that zigzag thing.
No, because we'll explain that. We need this area of the graph. Yeah, we need to get up to 1500, but we still need the 100 to 200 range.
Yeah.
And now we simply go ahead and plot our data. So what we have are corresponding values between our dependent and independent variables, and that makes coordinates that can go on our coordinate plane. So we're graphing it. We have the point 0, 0, because after 0 minutes, she's run 0 meters. We have the point 1, 150. Let's try to do this as...
Wait, how high did we go?
We went all the way to 10 minutes. After 2 minutes, she's run 300 meters. So you're looking at 2 on the horizontal axis and 300 on the vertical axis. And go ahead and continue plotting your points. When you're done, go ahead and think about question D at the bottom there, and do that just quietly and independently. Describe the shape of the graph. So what can you tell us about the data that we've just graphed, and where does it cross the vertical axis? Now, one thing we want to do before we talk about it too much is actually finish what we've done. So we've plotted our points, but this relationship is true not just at the 1 minute, 2 minute, 3 minute, 4 minute mark. It's also true at the 4.5 minutes, or 5 1/4, or 6 minutes and 10 seconds. It's always going to be true. So we can represent this relationship with a line. And mine has gone a little bit far. This part of the graph isn't included in anything.
Before you know you turn.
No, because I caught it before you.
What? Okay. Now we know that rule.
So go ahead and think about D. Describe the shape of the graph. Be specific. What kind of shape is it? And talk about where it crosses the vertical axis. All right, who wants to share what they thought for D?
What's vertical axis?
The vertical is up and down. These are your axes. Here's horizontal. Here's vertical.
Horizon.
Okay.
Horizon.
What would you like to share for a D? Describe the relationship. Describe the shape. What did we draw?
It's a line.
It's just a straight line. Okay. So it's linear.
Dope line.
And where does it cross the vertical axis?
At 0.
At 0. That's enough. So, we've related these two variables to each other. Time relates to distance, and distance relates to time. And now we need to write an equation to find the distance in meters that Suzanne jogs in T minutes. So now we're thinking, okay, how far has she jogged in Well, we don't know how long, but at any point in time within that hour, from 0 to 60, we could figure out how far she's jogged. How could we do that?
Make an equation.
We can make an equation. So what's our equation going to look like? Think about that for a minute quietly. All right, ladies and gents, it sounds like you have some good things happening. Jacob, would you care to share with us your equation?
It's D equals 150 times, no, times time, yeah.
Yeah, D equals 150 T.
No, it's
Right?
150.
So every
It's the same
T, every minute, she's going to run another 150 meters. So let's carry on. Use that equation now. So by the way, you've just done what lots of your math problems in your practice problems are going to be like. Develop an equation. Now use that equation. It's the same thing we've done for the last 3 units. Okay? Like we've done a lot of it. So here we go. Now we're just graphing it. Use the equation to determine how far Suzanne can jog in 40 minutes. Well, what do I need to do to determine that?
150 times 40.
Yeah, I need to, if I was doing this for homework, I would have to write D equals 150 times 40. For me, the neatest way to write it is using the brackets for multiplication. Find that very easy. Separates the numbers nice and clean. There's no X's that get confusing. And the final answer then? 6,000 meters. Good. Which is also 6 kilometers. Good job. Okay, G. Let's take this a little further. How far can Suzanne jog in 2 minutes? Well, we've already.
300.
That's an easy one. 300 meters. Oops, 300 meters. What happens to the distance when the time is doubled?
Add 150.
When the time is doubled. So T is not
Add
2.
300.
T,
Add
so we're going to add another 300. So let's not do that though. Let's think about, okay, we've doubled one side of the equation. We've doubled T.
So you have to double D. Double.
So D also gets doubled, okay? What happens to the distance when time is doubled? Well, it doubles. And the last little question there, what happens to the distance when the time is tripled?
It triples.
Triples. So the same thing is going to happen
We are
on both sides. This is direct variation, okay? The one is directly affected by the other. So on the top of page 7, we're going to take a few notes on what direct variation means.
actually like I don't think I know something.
We live in a rainbow tree.
You don't know the song at all.
Alright, you should have written direct variation at the top of page 7. Direct variation. A relationship between
Our relationship.
a relationship
Relationship I do not.
a relationship between two variables. That wasn't a mistake. So, in which one variable
It's an odd. Second.
is a constant multiple of the other. Okay, so the example we just talked about was direct variation. It's a relationship between two variables where one variable is a constant multiple of the other. So D is always 150 times T. No matter where you are on the chart, D is always 150 times C, where 150 is the constant multiplier. Okay? That's called our constant of variation. Constant of variation. This only is included in direct variation, which is what we're talking about this lesson. In direct variation, the ratio of corresponding, I'll explain this in a second, the ratio of corresponding values of the variables represented by the letter K, represented by K, or another way to say it, the constant multiple by which one variable is multiplied. Okay. I'm going to explain the second part first because it's a little bit easier. So the constant multiple by which one variable is multiplied. So if you look in here, the constant multiple by which the variable is multiplied is 150. So in this case, K is 150. Okay? Another way to find that is to take the ratio of corresponding values of the variable, which basically just means you're doing this. If I took 150 divided by 100, I'd get a corresponding ratio of 150 over 1, which is 150. Or I could take 300 over 2, which is 150. Or I could take 450 over 3, which is 150. Or I could take 600 over 4, which is 150. See what's happening? So we've created the ratio of corresponding values of the variable represented by K. We just found out that the constant multiple is 150. We could think about it in two different ways. Okay? So to get from 7 to 1050 is multiply by 150. We could also say 1050 divided by 7 is 150. Both ways will get us K. Alright? A couple more notes underneath constant variation. If, and try to figure out what this means as I'm saying it, if D varies directly as T, so D and T have a relationship where D varies directly as T, then the constant of variation, which is comma K, whenever you see that, it just means K is how we represent. K is the letter or the variable that we use to represent the constant of variation, is given by K equals D over T, or D equals KT. Now this is just another way of saying exactly what I just described to you. If you want to know what K is, take your distance, divide it by time. Do that again 3 times or 4 times, and if it comes out as 150 every time, then you know 150 is K. The other way to do it is find out, look at D, and say, okay, what did I have to multiply T by to get to my D? If it's the same every time, then you have a constant of variation. In this case, K equals 150. All right. Example 1, ladies and gentlemen, we have a family going on a trip. The Frederick family travels 250 kilometers to a relative's home. Okay, so that's the whole trip, 250 kilometers. The distance, noted by the variable D, is measured in kilometers, varies directly with the time T in hours. So what does that mean so far?
So D equals time.
D equals something times T. Not necessarily 250. All it means is that at any point in time, we can determine how far they've driven because they're going to drive a constant rate. Okay? If they're driving a constant rate, then after 1 hour, we know where they are. After 2 hours, we know where they are. After 20 minutes, we know where they are because they're driving a constant rate. Okay? Here we go. Find the equation relating D and T if D equals 43 when T equals 0.5. Okay, so they're driving for half an hour, and you can do this in your head pretty much. They're driving for half an hour, and they've gone 43 kilometers. So what's their rate of driving at kilometers per hour?
86.
So in half an hour they've driven 43.
21.8.
All right, so here's what it looks like, okay?
Looks like 21.
And underneath you're going to write a little note here, since D varies directly with T, so since it's a direct variation, T is independent, D depends on T, and it's going to vary directly, which means it's going to change at the same rate all the time by a constant multiple. We know that
You forgot a comma.
D equals
Don't mistake, Jonas.
K times T. How do we know that? Well, that was part of our definition for constant of variation when we did at the top of page 7. So we know every single relation here. D varies directly with T. That means D is going to equal T times some number. Okay? But we don't know what that number is yet. We're going to find out what that number is. So what we need to do is sub in what we know. And we're not going to use this one. We're going to rearrange to find K. So we can look at our definition for constant of variation, and we know that K equals D over T. Or we could just think about it and say, okay, how do I get K by itself? Well, it's being multiplied by T, so I divide both sides by T. Okay? That's all you did here to get this one. Now, we know that D is... What is D? It tells us the value.
It's the distance.
43.
43. And the time? 0.5. You have your calculators out. 45 divided by 0.5. Sorry, 43 divided by 0.5.
21.1.
86.
You're just timesing it by
Yeah.
2.
Wrong.
It's
Good.
86.
Okay?
Definitely 86.
86.
Therefore, the constant of variation is 86. And then we can make a note, this is their speed. 86 kilometers per hour. And what was our goal? Our goal was to find the equation. So therefore, the equation that relates D to T is what? If D equals KT, then what do we have? D equals, we know what K is now.
Oh.
D equals 86T. Now this equation will help us get their distance at any time during their trip. Okay?
Never make it.
Which is exactly what we have to do in question B. Question B says, use the equation that you've just determined to determine how long it will take for the family to reach their destination. So if we know that D equals 86T, what do we know about their destination?
It's 250 kilometers away.
It's 250 kilometers away. So I sub in that for D or for T?
D.
So I'm going to sub in D equals 250. That's going to be 250 equals 86T. And the question was, how long will it take for them to reach their destination? So now what do I have to do?
Divide 86 divided by 250.
Slow down. Use the proper language that we've been using all the last 2 weeks. What do I have to do? I want to get T by itself.
Ooh.
Do the same to the other. No, Ronnie, don't even say that.
Yeah, that's it.
I have to do the same
Isolate.
thing to both sides. Sure, I'm going to isolate t by doing the same thing to both sides. What am I going to do to both sides?
Divide by 86.
Divide by 86.
That's getting messed up.
So Maddie, I think that's the direction you were going for, but you said it wrong. So I want you guys to learn how to just say
I said
things.
9 hours.
Well, you're wrong.
T equals?
2.9.
You get, everyone should check it.
0, 6, 9, 7, 6, 7, 4, 4.
Mojo.
Yeah.
All right.
0, 6, 6, 9, 6.
Final sentence.
You have to put a little doopy thing over
It
the equal sign.
will take the Fredericks, or them, about 2.9 hours
Can you just say 3 hours?
Nope.
to reach
You
not
can't
true.
just round time.
their destination.
Valid point by Ronnie.
I'm not that.
What if they take pit stops? Yeah.
That's the only smart thing I've said.
All right, here we go. Example 2, hourly rate of pay. So we've done quite a bit of work with hourly rate of pay, like, you know, if Sam works for 6 hours and he gets $10 an hour and he sells bags of popcorn and he gets 40 cents per bag of popcorn, how much did he earn if he sold, yada, yada, yada. Yeah, we've done lots of that kind of stuff already. Now we're just graphing it. Okay, we haven't graphed it yet. So, Amir works part-time at a local bookstore. He earns $7.50 per hour. Does he earn anything per book? No, it doesn't say that. So
Would that be commission?
it would be some form of commission, and that's what we're going to learn about next time. But for now, we have a direct variation between the hours that he works and the amount of money that he makes. So there's nothing else coming in between there to confuse us. It's just, boom, he works 1 hour, he gets $7.50. He works 2 hours, he gets $15, etc. Okay? Describe the relationship between his pay in dollars and the time in hours that he works. Talk to the person directly behind you about that relationship. All right. You've had some guys.
Because you didn't say
Pull it together now.
Actually, that is false. I said
Boys and girls.
You said break. I told you like break.
Okay, let's go. To get, so let's just talk about how do we get
Board. No.
to,
There you go.
to get Amir's pay.
I'm gonna call him
What do we do? What do we do to get his pay?
Times the hours by the money.
Multiply the hours he works by his rate of pay, which we can put in brackets here is $7.50. And the way to use our proper vocabulary is if we call his Amir's pay, we represent that by P. So we'll say P varies directly with T, which is time. P varies directly with T. And what's our constant of variation? Go ahead and look back at what constant of variation means.
$7.50.
Nice. The constant of variation is $7.50.
Babies are balling.
Okay. We are going to graph it. So B, we're going to illustrate the relationship graphically and represent it with an equation. Now, for starters, whenever you're graphing something, we're going to make a table of values, okay? So we've got T, which is measured in hours, and we have P, which is measured in dollars, okay? Whenever we do our table of values, we're going to start with 0, okay? You know, this is tricky, but don't start with 1, start with 0. 0 gives us a lot of very important information. We're just going to, oh, you know what, actually, we're going to go by 2s. 0, 2, 4, 6, 8, 10. And let's fill in our chart. How much does he earn after 0 hours? $0. This is the key, by the way, to direct variation. 0 in the independent variable will match up with 0 in the dependent variable. Your graph will always go through 0, 0. Next lesson, it won't. Okay, next lesson we'll add a constant and you'll see how that affects it. After 2 hours, how much does he earn?
15.
4 hours?
30.
6 hours?
45.
8 hours?
60.
And 10 hours?
70.
And use your chart. We're going to, again, we're going to leave some room here. I'll make it so we can see our chart. I'm going to leave 2 squares on the left for my data labels and 2 squares on the bottom. What should we name the horizontal axis?
Hey. Or
Ooh.
Chart.
So basically what I'm asking is which of these are independent?
Independence time.
Time is independent. So our independent axis is t. And we need to get up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just bits for me. And pay, we want to get up to, well, we need to get up to $75, and we'd like to leave at least a little bit of space up there. So maybe get up to $80. I think we should be able to go up by tens. And then remember to label that axis as well. And that is pay. All right. In order to do our graphs even better, we can label the axes down here. Say this is time and tell that it's measured in hours. And then along the vertical axis, we can do the same thing. This is pay, and it's measured in dollars.
Why is it time A?
H.
For hours.
That's an A.
How's that an H?
And ladies and gentlemen, go ahead and plug in your coordinates. Plug in your data. You have 0, 0. You have 2, 15. And keep going. And we can draw a line through our points with a ruler, please. If you don't use a ruler on a quiz or a test, I will simply rip up your paper.
Oh, wow.
No, but I will dot marks.
Why?
Thank you.
Look, I use other things.
I know, right?
I can use my finger.
Why would I do that?
And now we're asking a question that we can use. Oh, we need to write an equation still. So we know our general equation for direct variation is we're going to put our dependent variable on the left with an equal sign. And then on the right is going to be our constant of variation times our independent variable. So in this case, our dependent variable is pay. It's P. P equals K times T. Okay? And we know what K is. What's K?
Constant.
What's the value of K? We know it. 750. So this would be our equation. P equals 7.5 T. Okay, so this is still part of B, drawing the graph and coming up with an equation. And C, now that we have an equation, we can use it. 1 week, Amir works 9 hours. Find his pay for that week.
Go to equation.
It would be
We just
67.
It equals 950. Or how much is it? 9.
equals
Oh,
all we have to do, guys,
command.
is rewrite our equation. P equals 7.5 times
T
T,
was
but
9.
now we know T is 9. chuck it in your calculator.
67 decimal 5. Do this.
67.9.
Okay?
Decimal.
Amir's pay
Point.
for 9 hours
The equation pay.
is $67.50. Your practice problems for this lesson are found on the bottom of the page. It's from page 509 in your Math Power textbook, numbers 1 through 6, and there are 3 problems on the next page, on page 9, that you can do. Okay, do those in your notebook as well.
Are we dismissed?
You are dismissed.
Thank you very much.